This is the screencast for section 6.2, example 2. Now, a lot of these properties of integrals you already know. Some of the new ones we're going to focus on here are over here. As a matter of fact, in example 2, we're going to verify antiderivative formulas, specifically the antiderivative of u to the negative 1 du. We need to verify that that is equal to the natural log of the absolute value of u plus c. All right, so the verification for this one is pretty much straightforward because we now have the fundamental theorem of calculus to connect derivatives and antiderivatives. I can simply say, since the derivative, so with respect to u, of the natural log of u and then plus c is 1 over u plus 0, in other words 1 over u, I can then say that the antiderivative of 1 over u du is backwards, the natural log of the absolute value of u plus c. Now we use absolute value here because you can't take the logs of negatives, well, or 0, but we want to avoid that possibility, so we're assuming the absolute value in this situation so that we don't have to deal with that part in the domain. Part B, we're going to follow the same process. We're going to start with the end and take its derivative. So we're going to take the derivative of u, natural log of u, minus u plus c. Alright, so the derivative of u natural log of u, well, that's going to be product rule. So the derivative of u is 1, and then leave the natural log of u alone, plus, now I have u times the derivative of natural log, which we said was 1 over u, as we discussed in part A also. And then now we're past the product rule. Now I'm still at minus u. The derivative of minus u would be minus 1, and the derivative of c is plus 0, which I didn't have to write, but that's okay. Now a little bit of simplification, and I get the natural log of u. Alright, so now we can say that since the derivative of u times the natural log of u minus u plus c is the natural log of u, then we can say that the antiderivative of the natural log of u du equals u times the natural log of u minus u plus c. So we just work that backwards. Now I know you're saying, why absolute value sometimes and why not absolute value other times? Well, here's the thing. This problem B actually gave us the antiderivative of the natural log of u as part of the initial problem. So in this case, if that's where I was supposed to start, proving that that equals this, I can assume then that u had to be positive, otherwise it wouldn't work. I wouldn't have been able to take the natural log in the first place. That was not the case over here in part A, where u to the negative 1, u could have been positive or negative. That's why we used the absolute value when we took the antiderivative. The now try problem number 11 says use differentiation to verify the antiderivative formula. So we are going to take a derivative to verify this, which means if the antiderivative of this equals that, we have to use the fundamental theorem and take the derivative of the second part to equal the first part. So that's what I'm going to do. I'm going to take the derivative of inverse tangent of u plus c. Alright, so the derivative of inverse tangent, if you remember, is 1 over 1 plus u squared, and then the derivative of c is 0. Which really then is just 1 over 1 plus u squared. Alright, so now, since the derivative of the inverse tangent of u plus c is 1 over 1 plus u squared, that means the antiderivative of 1 over u squared du has to be the inverse tangent of u plus c.